Hi, our topic for today is about integration of hyperbolic functions. So at the end of the lesson, you should be able to identify the appropriate integration formulas of hyperbolic functions for any given integrals and evaluate integrals of hyperbolic functions. Okay, so before we discuss how to evaluate integrals involving hyperbolic functions, let us first define the hyperbolic sign and hyperbolic cosine. Hyperbolic sign is e to the x minus e to the negative x all over 2, while hyperbolic cosine x is e to the x plus e to the negative x all over 2. Observe that for hyperbolic cosine x, the operation in the numerator is addition, and for hyperbolic sine x, the operation in the numerator is subtraction. Okay, the following are the different identities involving hyperbolic sine. Hyperbolic tangent x is hyperbolic sine x over hyperbolic cosine x. Hyperbolic cotangent x is hyperbolic cosine x over hyperbolic sine x. Observe that the reciprocal of hyperbolic tangent x is the hyperbolic cotangent x. Similarly, hyperbolic secant x is defined as 1 over hyperbolic cosine x, which means that the reciprocal of hyperbolic secant x is hyperbolic cosine x. Next is the hyperbolic cosecant x, and this is equal to 1 over the hyperbolic sine x. Again, the reciprocal of hyperbolic cosecant x is the hyperbolic sine x. Next, we go to the other identities, such as hyperbolic cosine squared x minus hyperbolic sine squared x equals 1. Next, 1 plus the hyperbolic tangent squared x is equal to hyperbolic secant squared x. Next, the hyperbolic cotangent squared x minus 1 is equal to the hyperbolic cosecant squared x. And then for the double angle identities, the hyperbolic sine 2x equals 2 times the hyperbolic sine x times the hyperbolic cosine x. And the last but not the least is the hyperbolic cosine 2x is equal to the hyperbolic cosine squared x plus the hyperbolic sine squared x. Okay, so let us now discuss the integration formulas of hyperbolic functions. So the first formula is the integral of hyperbolic sine u du equals hyperbolic cosine u plus the constant c. And you can verify this formula by taking the differential of hyperbolic cosine u, which is equal to hyperbolic sine u du. So when you take the integral of both sides, we get the first formula of the hyperbolic functions. For the second formula, the integral of hyperbolic cosine u du is hyperbolic sine u plus the constant c. Now, you can verify on your own that the integral of hyperbolic cosine u du is equal to hyperbolic sine u plus the constant c by taking the differential of hyperbolic sine u and then taking the integral of both sides. So, you get this formula. Okay, the third formula is the integral of hyperbolic secant squared u du, and this is equal to hyperbolic tangent u plus the constant c. Next, we have the integral of hyperbolic cosecant squared u du, and this is negative hyperbolic cotangent u plus the constant c. Next formula is the integral of hyperbolic secant u, hyperbolic tangent u du, and this is negative of hyperbolic secant u plus the constant c. So this is product of hyperbolic secant and hyperbolic tangent. Next formula is the integral of the product of hyperbolic cosecant u, hyperbolic cotangent u du. And this is negative of hyperbolic cosecant u plus the constant c. Next formula is the integral of hyperbolic tangent u du. And this is equal to the natural log of hyperbolic cosine u plus the constant c. So take note of the absolute value. Next, the last but not the least is the integral of hyperbolic cotangent u du. And this is equal to the natural log of the absolute value of hyperbolic sine u plus the constant c. Okay, so to learn how to apply the formula, so let's have the following example. So number 1, suppose we are asked to evaluate the integral of x times the hyperbolic second squared of x squared plus 3 dx. So as you can see, because this integrand contains hyperbolic second squared, so we can use formula number 3 now from this list of integration formulas of hyperbolic function, wherein the integral of hyperbolic second squared u du is hyperbolic tangent u plus the constant c. So in this case, because the argument is x squared plus 3, so by substitution, we let u be x squared plus 3. And then taking the differentials of both sides, so du is 2x dx. Okay, so as you can see, x dx is part of this integrand. Now we have x dx. But 2 is missing, so we have to solve for x dx by dividing both sides by 2. So we get x dx is du over 2. And then this integrand can be written as product of hyperbolic second squared of x squared plus 3 times we isolate x dx, so we have this product x dx. And then by substitution, because we let u as x squared plus 3, so you can write this as integral of second squared u times the value of x dx, but x dx is du over 2. So we replace this by du over 2, but because 1/2 is constant, so we factor this out. So we have the integral of hyperbolic second squared u du. And then recall that from the formula, the integral of hyperbolic second squared u du is hyperbolic tangent u plus the constant c. So therefore, the integral of hyperbolic second squared u du is hyperbolic tangent u times the constant 1/2 plus the constant c. But again, same in the previous discussion, because the given integrand is in terms of x variable, so we have to rewrite the final answer in terms of x variable. So in this case, since the value of u is x squared plus 3, so the final answer is 1/2 times the hyperbolic tangent of u, where u is x squared plus 3 plus the constant c. Okay, so let's have another example. So suppose we are asked to evaluate the integral of hyperbolic cotangent squared x dx. If you look at the table of integration formulas of hyperbolic function, there is no direct integration formula. So what we have is the integral of hyperbolic cotangent u du of degree 1, but there's no degree 2 for hyperbolic cotangent u. So what you have to do is you have to use the hyperbolic identities. You have to rewrite the hyperbolic cotangent squared x using this identity listed on this table of identities, wherein the hyperbolic cotangent squared x minus 1 is hyperbolic cosecant squared x. So to solve for hyperbolic cotangent squared x, you transpose negative 1 on the other side. So we get hyperbolic cotangent squared x equals 1 plus hyperbolic cosecant squared x. So we replace this hyperbolic cotangent squared x by these identities. 1 plus the hyperbolic cosecant squared x. And then to integrate this, we separate this into two integrals by distributive property. Okay, so you can write this as the integral of dx plus the integral of hyperbolic cosecant squared x dx. And recall in the discussion of the basic integration formulas, the integral of dx is x, and the integral of hyperbolic cosecant squared x from this table is negative hyperbolic cotangent u plus the constant c, where u is x and then your du is dx. So we can use this directly to evaluate the integral of hyperbolic cosecant squared x dx. So from that formula, the integral of hyperbolic cosecant squared x dx is negative hyperbolic cotangent u, where u is x, And then, therefore, the final answer is x minus the hyperbolic cotangent x plus the constant of integration c. So in summary, the differential formulas for the hyperbolic functions lead directly to the integral formulas of hyperbolic functions. Like for instance, when we take the differential of hyperbolic sine x, this is equal to hyperbolic cosine x dx. And then taking the integral of both sides, so we get the integral formula for hyperbolic cosine x dx, which is equal to hyperbolic sine x plus the constancy.